Hey folks, hope you're doing well. Today we're looking at the second mini lesson on Unit S, Simple Linear Regression. We're looking at pages S5, 6, and 7, and they start on page 153. So in the first lesson we took a look at the population regression model and line, and then said that we don't have access to the whole population, and so we of course come up with a sample, and we come up with a sample model and the line. But the question is, how do you come up with the B0 and the B1, which are the intercept and slope for the sample regression line? Well, let me show you how the formulas work. So on page S5 here, I've drawn a couple of little graphs right here. And they're supposed to look pretty much the same. I know they don't look exactly the same, but pretend that they do. Now, here's the question. Which line is better at showing the relationship between x and y? Is it that one, or is it that one? Now, it's pretty obvious that it's the second one, but the question is why? Like, what measure would you use to say that it's a better line? And of course, informally, you would say, well, it fits the points better. And so that's absolutely true. Whereas the first one here, it doesn't. But what's the measure of it being a good fit? Well, it has to do with the error terms. Remember, the errors are the vertical distance between the points in the regression line. So if we take a look at this one here, you can see that the vertical distance between the points in the line are quite large. Whereas over here, they're quite small. Now, you can't just simply average out those errors, because you've got a bunch of negatives and you have a bunch of positives, and they'll just turn out to be zero if you've done the calculations correctly. So there's got to be a better way of handling that. And so what we do is, instead of dealing with the average of the error terms, we take a look at the squared error terms. So we add them all up, and we want to minimize the sum of the squared error terms. Now, this part down here might scare a few of you, unless you're taking calculus. And even then, you might look at it and say, hey, we always deal with x's and y's in calculus. But you can actually take a look at this equation here, which is the yi's minus the y hats, and minimize them with respect to B0 and B1. Now, I'm not going to walk through the calculus of that. You can do that yourself if you're interested. You don't have to know that for an exam. But basically, we end up with two equations. They're called normal equations, and we can equate them to each other and solve for B0 and B1. So again, you don't have to know that, but that gives us these two equations down here. So the first one, you'll notice, actually looks really similar to our equation for R. We could actually write this as the sample covariance of x and y over the sample variance of x. And you'll remember that R was equal to, same numerator, sample covariance of x and y, over the standard deviation of x times the standard deviation of y. So the only thing that differs is actually the denominator. And in this particular case, you're just dealing with the standard deviation times itself, right, squared, whereas down here you're looking at the standard deviation of x times the standard deviation of y. This guy right here, we can expand that out to say that B0 is equal to y bar, which is the sum of the y's over n, minus B1, the sum of the x's over n. Now, that's a really important relationship here, because it has no error term. And what that means here is that if we take a look at, let's draw in a couple lines here. So I'm going to have, I'm going to have a line that goes like that, and a line that goes like that. And this is going to be the y bar line, and this is going to be the x bar line. And according to this equation, the sample linear regression line will go through that particular point, x bar, y bar. So it's got an intercept, and it's got a slope. And so we've got the y hat values are equal to b naught plus b1 times x. And it goes through the point x bar, y bar. So given that then, let's take a look at a couple of problems. So we were introduced to this one back in Unit C, the age and the push-ups. And here we're asking the question, does the number of push-ups, the other way around, does the age of a person, the x variable, determine the number of push-ups that a person can do? Now back in Unit C, and specifically, let me just find that page here. So we first encounter that problem in page C7. So see page C7. And we'll see where we calculated the R there. But there what we did is we came up with some summary value. We came up with some numbers here. So 361, 1156, and 646. Remember, the 361 is 19 squared. The 1156 is 34 squared. And then the 646 is 19 times 34. And you can do that for every value, every row, pardon me, all the way down. And then we'll end up here then with the sum values down here. So I'm just going to write those in. So you do that calculation all the way down each column. And this is what we end up with. And again, these are the same numbers that we ended up with back in page C7. So the sum of the x's is 503. The sum of the y's is 261. Sum of the x squares is 25,921. Sum of the y squares is 6531. And the sum of the xy's is 9658. That's a 5. Okay. Now, part A here says draw a scatter plot. I've already done that here. And so what I've got is the age is your x variable, and then your push-ups is your y variable. And then what I've done is I've drawn a bunch of little green x's here, which are the actual points of the line here. So 1934 then would be this guy up there. Okay, so that's your first observation. Now, if we were to draw a regression line through here, it would look something like this. It actually has an intercept, which we're going to calculate in a moment, of about 33. So it actually looks something like about that. And it has a negative slope. So it has an intercept here, which I'm going to show you how to calculate of, let me get back to the right page here, 32.86. So 32.86, and then it has a slope of minus 0.2265. So let me show you how I calculated that. All right. So the first thing that we do is we calculate the slope, B1. And from that, we can then get the intercept. The slope is equal to the sum of the xy's minus the sum of the x's, sum of the y's, over n, divided by the square root, not the square root, pardon me, just the sum of the x squares minus the square of the sum of the x's over n. Right? If we were calculating r, and I'll do that again in a moment here because it asks us to recalculate that to just remind you that. It has the same numerator, but we would be taking the square root of the sum of x squared minus square of sum of x times n, and then a y term as well. All right, let's plug in some numbers here. So the sum of the xy's is 9658 minus 503 times 261 over n, which is 10, I believe. Let's just count those up here. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's a good thing I checked. It's actually 12. There we go. So the n is equal to 12. Remember, it's not 24 numbers, it's 12 pairs. And then the denominator here is some of the x squares, which is 25, 921, minus the 503 squared over 12. And when the smoke clears, you're going to end up with your slope of minus 0.265. All right, then what we do is we calculate the b naught, which is equal to the sum of the x's, sum of the y's, pardon me, over n, minus b1 times the sum of the x's over n. So in this case then would be sum of the y's. I wish you would stop doing that. Oh dear. Okay. So the sum of the y's then is 261 over 12 minus a negative 0.265 times the sum of the x's, which is 503, over 12. And that equals, what did I say, 32.862. So we can express then y in terms of x this way. Y hat is equal to 32.862 minus 0.265 times x. Or what a lot of people do, and I actually prefer this, is if you write in the actual names of the variables. So push-ups hat is equal to 32.862 minus 0.265 times age. All right. Now, the last thing that this one asks us to do here is calculate R. What I could say is just go back and see page C7, but we'll do a calculation of R down here. So R is equal to the sum of the xy's minus the sum of the x's times the sum of the y's over n, and then the square root, the sum of the x squares minus the square of the sum of the x over n times the square root of sum of the y squares minus sum of the y squared over n. So that is, what do we got here? 9658 minus 503 times 261 over 12 over, and then we've got square root of 25,921 minus 503 squared over 12. And then we haven't used the sum of the y's, y squared values. It's 6531. So you don't need that guy for just calculating the b naught and the b1, but you do for calculating r. That's a 261 squared over 12. And that gives you, what did we get for that? Minus 0.631. There we go. And that's what we got on page C7. So that's that. All right, let's take a look now at a different problem here. This is taking a look at the size of the house and the price of the house. So the price of the house then is Y, and it's in thousands of dollars, and the size of the house is X, and that's in hundreds of square feet. So here's our observations. There's 1, 2, 3, 4, 5, 6, 7, 8. So n is equal to 8. And then we come up with our values here. So 15 squared gives you 225. 145 squared is 21025. And then 15 times 145 gives you 2175. And then we're going to get our summed values here. So the sum of the x's is 165. Sum of the y's is 1334. Sum of the x squares is 3855. Sum of the y squares is 241, 394. And sum of the xy's is 29,611. All right. Let's actually calculate the B1 value first. And so we're going to have the sum of the x's, sum of the xy's, minus sum of x, sum of y, over n, over sum of the x squares, minus square of the sum of x, over n. So that's going to be 29,611 minus 165 times 1334 over 3855 minus 165 squared over 8. Oh, you know what? I forgot to divide this up here by 8. Can you see that? So that last term is 165 times 1334 divided by 8 in the numerator. And then you end up then with a slope here of 4.641. Now the intercept, B naught, will be the sum of the y's over n minus B1 times the sum of the x's over n. And that's going to be equal to 1334 over 8 minus 4.641 times 165 over 8. And that's going to give you an intercept of 71.025. So what we can say, the relationship between the two is that the price, oops, what's that? The price hat, that's your y, is equal to 71.025 plus 4.641 times x, and x is equal to the size of the house. So the interpretation of that is that for every, what was the units here of x? So every 100 square feet, so in this case for every 400 square feet, then their price would go up by $71,000. Back here, I should take a look at that age and push-ups one again. What that's saying here is, here's our line right here. So that's saying that for every 1 year increase in age, the number of push-ups goes down by 0.265. So what that really means is about every 4 years or so that you increase in age, the number of push-ups that you can do goes down by 1. Now this here, where it says 32.862, that doesn't mean that an infant, a newborn, can do 32.862. If you take a look at the range of the ages here, it looks like the youngest is 18, so we're really talking about a range that looks like that to here. And so really you'd want to find out what this value is for an 18-year-old. That should be closer to 18 there. And then it goes down by about 1 push-up every 4 years. All right? So similarly here, I mean, you're really looking at the smallest house is about 1,300 square feet. And so it's only good within a certain range. You can't extend that right down. We end up with an intercept here of about 71. 71 and then a slope of 4.64. Oops, sorry, I lost it. Oh boy, now it's really getting messed up. Okay. All right. So we'd end up with a line that looks something like that. And it's probably that I just didn't draw it very well, but it has an intercept of about 71. And it has a slope here of 4.64. And remember, it's good within a certain range from about 1,300 up. So that's what we've got. Oh, last thing here, I guess, is to calculate R. So I asked you to do that as well. Let me do that in a different color. R is equal to the sum of the xy's minus sum of x, sum of y over n. And the denominator then would be sum of the x squared minus square of sum of x over n times the sum of the y squared minus the square of the sum of y over n. So very similar to calculating the B1 above. So you'd have 29,611 minus 165 times 1334 divided by 8. Didn't forget the 8 this time. And then your denominator is going to be same first term as above, but under a square root sign. So 3855 minus 165 squared over 8 times the square root of 241,394. That's this guy right up here at the top of the screen. Minus 1334 squared over 8. And when the smoke clears, you're going to get an R of 0, so plus 0.717 or 0.72. Okay? So that is a fairly strong positive correlation. As the size of the house increases, so does the price. And I think that's where I'm going to